Alright folks, so from yesterday we talked about what makes something bendy, right? When something bends a lot, what makes it stiff or bendable, right? Well, one thing is definitely the moment of inertia. And I think that's something you guys already knew. Like if you take a thin piece of wood and you're able to bend it, and it bends a lot. And then if you take a thicker piece of wood, you might be able to stand on it and it bends a little bit. And if you take even a thicker piece of wood, it looks like it might not even bend at all. It does bend, okay? So any piece of wood, I don't care how thick it looks, when you stand on it, it's going to bend. It just might bend so small that you can't even tell, but it will bend. And that stiffness has to do with the cross-sectional area. So when I say the cross-sectional area, it's this area right here. So we don't really care about how long it is. Moment of inertia is about this area right here, that little cross-section at the end. That's what we're looking at. And to calculate it, all we need is the base and the height of that cross section. So what's the base in inches here and the height in inches? You take the height and you cube it, so times it by itself 3 times, and then multiply it by the base divided by 12, and that gives you the moment of inertia. See, there's a cross section right there. We did a calculation and it turned out that this joist, because it's really tall right here and really thin, it had a very strong moment of inertia. So if you stand on it, it doesn't want to bend. But if I rotate that around this way, it will bend a lot, because now it's only 1.5 inches height right here and 5.5 inches wide. And when we redo the math, even though it's the same piece of wood just laying sideways, the base and height are different, and thus it changes a lot. So now the new stuff right here, we'll see bouncy. Now the new stuff right here, what I want to cover is this. What else matters when you're talking about how stiff it is? What else matters? And what does matter is this modulus of elasticity, which we just call E. Modulus of elasticity is what is the material made out of, like how bendable is the material itself. And of course that matters. You guys know that if I take a long piece of wood and stand on it, it's probably going to bend. But when I take a long beam of steel, it will also bend, but probably so little that you won't even be able to tell, maybe not even measure it with the ruler or something. So it's really stiff, right? So the material itself matters. So is it made out of plastic? Is it made out of wood? Is it made out of metal? Of course, modulus of elasticity, all that means is the chemical makeup, like what is the thing made out of? And depending on what it's made out of, it will bend more or less. Modulus of elasticity principles. See, so here's now 2 different beams, both of them joists, both of them the same cross-sectional area. As you can see right here, the cross-sectional area, the width and the height are the same. But the materials are different. One's Douglas fir and one's ABS plastic. It's a certain type of plastic. There's lots of different plastics, by the way. There's not just one. What distinguishes one beam? Will beam A or B have the greater resistance to deformation? It looks like the plastic one is bending a lot more, right? Because plastic is not as strong as the wood. And why are they different? Why do they bend more than different? Because they have different modulus of elasticity. Now we're going to calculate this right here. Here's our new equation. Now this is the last thing for this unit here, and we're going to calculate delta max. And what that means is, it just looks like a big word, but all it means is how much is it going to bend. Like, is it going to bend just a little 1/4 of an inch, or is it going to bend a 1/2 an inch, or a whole inch, or 3 inches? How much is it going to bend? So if I stand right in the middle of this object, how much will it sag? Oh, it's going to sag down like a 1/2 an inch, when you stand on it, because you're a heavy guy. So what matters is, what do you think matters? Everybody look at this. There's only 1, 2, 3, 4 things that matter. Please pay attention. I think this makes really good common sense to you when you read this. So if I stand right in the middle of A or B, it doesn't matter which one. So when I stand on the middle of one of these, how much it bends matters on 4 things. Everybody look. Force. How much do I weigh? Of course, doesn't that matter? The bigger I am, the more it's going to bend, right? If I take a little tiny light person and stand them in the middle, it's not going to bend as much. So of course, this F matters. Force is how hard are you pushing in the middle. What else matters? The length. The length. Of course that matters, because the length, the longer this thing is, the more it's going to sag, right? Like if I take a little 2 foot long piece of wood and stand it up between bricks and stand on it, it's probably not going to bend too much. But if I take a big, gigantic, long, 10 foot long piece of wood and then I put bricks on each side to hold it up and I stand in the middle, it's going to bend a lot, right? Um, put it this way, folks. I want to ask you a question. I think everybody here at one time or another, maybe because you're raging over a math problem, probably broke a pencil, right, with your hand? Yes? Did you guys all realize that breaking the pencil was a lot easier when it was full length, right? Weren't you able to bend it a lot easier when it was like longer? Because when you break the pencil and it gets shorter, isn't it harder to break? Did the pencil change its material? You're not changing how much force you're applying, you're still trying hard to break the pencil, right? The modulus of elasticity of the pencil is the same. It's still made out of wood and graphite in the middle, right? The pencil didn't change. And this right here, the I, do you guys remember I? We calculated that yesterday. That's the moment of inertia. That doesn't change of the pencil. Does the pencil get thicker when you crack it? No, the pencil didn't get thicker. So the only thing that changes when you break your pencil in half is the length of the pencil got smaller. And thus now it's not going to flex as much. It's going to be harder to break it because it's not going to want to flex that much anymore. So yes, how hard you push on a piece of wood or something or material is going to bend it more. The length of the material, the longer it is, the easier it is to bend it. E, the modulus of elasticity, what is it made out of? Is it made out of wood, metal, plastic? That matters. And then I is the moment of inertia. We did that yesterday. Of course that matters. That's how thick it is, right? Like the makeup, the chemical makeup of, like, not the chemical makeup, I should say, the physical, like how wide in the base, right? That matters. So, that being said, let's do a calculation. Look at the information given down below, folks. It's beam A right here. It's made out of Douglas fir. The length is 8 feet. The I is 20.8. That's if you guys remember what I is, that's the moment of inertia. We calculated that yesterday. Remember, we got like 21 and 1.5 and stuff like that. It depends on this little cross section right here. E, modulus of elasticity. This one you have to kind of look up. Look up Douglas fir and look up the modulus of elasticity. It's around 1.8 million. Sometimes it's 2 million, depending on where you got your wood from and stuff. It changes a little bit. And then load. How heavy is the person standing in the middle? 250 pounds. All right. That's a big person. All right. So there's the equation. Look at the work. We put the force right here, 250 pounds right here. So we put 250 pounds of force here. L is 96. It has to be in inches. So what did they put? They put 8 feet here. Don't forget to times that by 12 and put how many inches. Because remember, you have inches here. Pounds per square I inch. Inches to the 4th power. So this has to be inches too, okay? So just take this 8 feet, times it by 12, you get 96. There we go, but don't forget to cube it. And then 48 times your E, that's whatever the material is. You have to kind of look that up. But in your problems, they'll be given to you. And then, of course, the I, which either is given to you in this problem, right? They gave it to you, or you might have to calculate it like you did yesterday, where you look at the what is it, the base and the height, and you do a little math problem, divide by 12, right? So here we go. You have to do this math. Now don't multiply this to the 4th power. That's the unit. See, this one you have to cube, right? You see that 3? But you don't have to do anything here. You just take this number times that number times that number. So the answer is this, 0.12. If you want to see the proof for that, here's how I would do it. I'm going to pull up a calculator just to show you, to walk you over it. And actually, I'm going to do this problem for you, okay? But before I do that, we're going to look at this one. Here's the same piece of wood. It's not wood, it's plastic this time, but it is 8 feet. It does have the same cross-sectional area, like the moment of inertia that we did yesterday. Look at it, it's the same thing. It's the same length, but the E is a lot smaller. It's a different material, right? And the same person is standing on it. What is it? How much does it bend? A half an inch. How much was the other one? 0.12 inches. So not even not even 1/8 of an inch, almost an eighth of an inch. This one bent a half an inch. So a huge difference, 4.24 times more. So one's going to bend 4.24 times more than the other one. And why? Only because of the material, the E, the modulus of elasticity. They're different materials. One's wood, one's plastic. All right. So I'm going to do a quick practice problem here with you guys, and then set you loose. So in today's practice problem, we are going to look at that one piece of wood that's like this, and that's a pretty good drawing, I guess, good enough. And if you look, it said it was 8 feet long, and it said the eye was equal to 20. I have it right here on my screen. Give me a second. I have it here. There we go. It was 20.8. And then if you want to know the unit, it's inches to the fourth power. And this one, the unit is feet. And somebody stands on the middle and they weigh 250 pounds. And then they call it pound forces. They just put an F there to say it's like a force, not a weight. And then what else do they give you? Oh, and the E of this material, because it's Douglas fir, is 1.8 million. So 1,800,000. And I think that's all they gave you, yeah. But the equation is this: delta max. Delta means change in max, so this is just how much it's going to move, like how much will it bend, and that's equal to the force times the length cubed divided by 48. That number always stays the same. Divided by 48 E times I. Okay, so doing the math problem, we get force 250 pounds. That's how heavy someone's standing on it. The length of this thing is 8 feet, but 8 times 12 inches, 8 feet times 12 inches is equal to 96 inches, because there's a 12 inches per 1 foot, and if you do a little conversion here, that's how you figure out how many inches. So just take your feet and times it by 12 to figure out how many inches it is, because this length has to be in inches, okay? That's one mistake I've seen students make a lot. So 96 inches. And then don't forget to cube that. That's going to be super important. And then on the bottom you take 48 times E times, I already know the E, don't I? I don't need to write E. I know what E is. E is right here. 1,800,000. It's a big number. It's pretty strong. Imagine what steel is. Steel would be way bigger than that, right? Because steel doesn't bend. And then 20.8. Alright, so here's what we're going to do. We're going to do the top number first, okay? So 96 cubed. So pretty much that's 96 times 96 times 96. It's 884,736. 884,736. It's a big number. So that's that number there. And then times 250. And then let's just do all the bottom work right now, since we already have this calculator open. Let's clear this out. And we'll go 48 times 1/8. I think I went too far there. 1/8. I did it again. I get too happy with those zeros. There we go. So I did 48 times this is equal to that. Then we're going to times it by the 20.8. And then I get, whoa, that's a big number. What is it? 1,797, 120, 3 zeros. That's a big number. All right. And then let's finish this problem on top right here. This 250 times that number. I should have done that before, but we'll just do it now. 250 times 884,736. 736, and we get to 221.84000. And then on the bottom we still have the 1797120000. Alright. Alright. Now, let's finish it off. Let's divide the two. Luckily, I have this top number right here already in there, so I'm going to push divided by this bottom number. Let's type it in. 1797120000. Let's push equal. Yes, we got the right answer. 0.123. 0.123. And this is inches, of course. That's what our delta max is equal to. I was hoping I'd get the right answer, and I'll have to do this all over again. So if you remember, that was the answer. So I got 0.123. They said the answer is 0.12. That's how much it's going to bend. So really, you're looking at, so by the way, this is what it would look like. So here's a piece of wood. They're standing on this, right? And so if they have this piece of wood, and the person right here, they weigh 250 pounds, this is going to sag down. And so if you, let's say you put a brick right here and a brick right here, and then let's take them off there real quick. So he's not standing on it, right? And if you measured this, ooh, I have the eraser. How did I do that? Oh. So if you measure this distance right here, let's say you measure it to be 0.552 inches, okay? So that's so from the floor right here to the wood, it's that. Once they stand on it and they weigh 250 pounds, given this information, this thing will now be this much less, right here. What was it? So you would take 0.552 minus the 0.12, and then you would get the what's that answer? 0.540 inches. So I don't know how much gap there was. It doesn't say that. That doesn't matter. But the point is that it's going to flex that amount. So however much gap there was here before, it's going to bend that amount. Now it's only this amount. Now it doesn't sound like much, and maybe that doesn't matter, but that's what this is used to calculate. So one quick overview is to calculate this. All you need to know is how heavy is the person, right? You need to know how long is this big beam of wood. Is it 10 feet long, 8 feet long, whatever? And then don't forget to cube it. 48, that's always the number there. Just like yesterday, the number was always 12, right? Modulus of elasticity. You need to know what material the wood, the material is made of. Is it Douglas fir? Is it a piece of pine wood? Is it oak wood? Is it plastic? Is it steel? You need to know that, right? Because those materials bend differently. And then, of course, you need to know the modulus, not the modulus, the moment of inertia. We calculated this yesterday, right? And what does that depend on? It depends on this cross-sectional area right here. Like how thick is the wood, right? Mainly what it is, it's what's the base and the height. That's what they want to know, right? The height and the base. And that's what it matters, because as this changes, like the cross-sectional area, then this I changes, so that matters as well. And that's pretty much it. And that's all I have for you as far as